Cool. Can everyone read what's on the screen okay? Should I make it bigger? Should I make it smaller? Slightly bigger, okay? Is that okay? Cool. Okay, thank you, Alex, for the introduction. So yeah, I'm going to tell you about the basics of Lean. I'm going to assume you know nothing. If you do know something, then feel free to ignore what I'm saying completely. Not too much, but mostly. And on this link, there are some exercises which you can work through, which you can do during the practice sessions, and all the tutors can help you with that. Or if you don't want to listen to me, you can start on them now. Okay, so like Alex was saying, Lean is a dependently typed language that we use to help verify things in maths. So what does it mean to be a typed language? It means every expression you write down has a type. For example, 2 is a natural number, and I can use this command #check to tell me the type of something. So right now, Lean is telling me that 2 is a natural number, that 17 plus 4 is a natural number, that pi is a real number, and this last example is e, so the real exponential of 1 is also a real number. Okay, so we have these expressions, we have these types. But these types on the right-hand side are also expressions. So they should have a type. So what's the type of natural numbers? Well, that's itself a type. So the natural numbers are a type, and the real numbers are a type. Now, just using built-in things isn't so interesting, so we're going to make our own. My favorite number, 7, and I've called it my favorite number. Def lets me define something. I've given it a name, I've given it a type, and I've said this is the expression I want it to be. We can also make another definition. But if you're not sure what the definition is yet, you can put sorry. Sorry is this global placeholder for Lean where you can basically put it in and tell Lean, I'm going to fill this in later. I'm not sure what it is yet. Because when I was writing this file, I don't know what your favorite number is. What's your favorite number? Anyone? 37. Okay. The canonical Lean number. Okay. And once I've made this definition, I can then check that it has the type I claim it does. So I can check it. We also have the option of not giving it a name, which is what example will do. So these are the two things to start off with. We have definitions and we have examples. This isn't very interesting maths, though. So how do we actually do maths? Well, there's another important type called prop. The type prop contains all the propositions. So all of the elements of type prop are propositions, stuff which you could hopefully prove, maybe sometimes not prove. But it does include the false propositions. It also includes the open questions. So 2 plus 2 is 4 is a prop. E is less than pi is a prop. But 2 plus 2 is 5 is also a prop. So the type of propositions doesn't care whether your thing is true or false. It just consists of all the things that could be true or false. It also includes open problems. For example, is e plus pi irrational? And is my favorite number equal to your favorite number? Well, now we know the answer to that. But earlier, I didn't know. I can also write down some more difficult propositions. I think that hopefully fits on the screen. Let me just put it on a new line. So I've got a slightly more difficult proposition here. I'll read this out carefully. I won't go into too much detail on what the quantifiers mean, because we'll see that more in Jacob's session next. So this is saying for all n in natural numbers, there exists a p where n is less than or equal to p, and p is prime, and p plus 2 is prime. So this statement you might recognize as the twin prime conjecture. And I can write this down as a proposition and give it a name, in this case, my difficult proposition, because it's quite difficult. I can also make some other ones, so here are some more examples. My easy proposition is quite easy to see that it's not true, and my very easy proposition, which is hopefully pretty clearly true. It's important now to distinguish between the key thing to notice here is that earlier I had this type of natural numbers and had elements of it, which were natural numbers. But if P is itself a proposition, for example, my very easy proposition, then I can give expressions of this type, just like 3 was an expression of type natural numbers. An expression of type P is a proof of P. So if I can give some expression which has type P, then I have proved P. So for example, can I give an expression of type 2 plus 2 equals 4? It turns out I can. It's REFL. I'll explain what this means a bit more in a moment. But right now, what we can think of is I have an expression of type 2 plus 2 equals 4. Therefore, I have proved 2 plus 2 equals 4. I can also prove 2 plus 2 is not equal to 5. And I can use this tactic called simp. Again, I'll talk about that more in a second. And so this is how I can disprove something. And just like before, I can use sorry if I'm not sure what the proof is yet. So here is a conjecture called the Erdős-Strauss conjecture. And this is an open problem. So I'm just putting sorry because we don't know the proof yet. We don't even know if it's true. One thing to mention here is that I can also put my assumptions before the colon. So let me go through that a bit more carefully. In this first statement, it's a logical statement which says, for all n, 2 is less than n implies some existential. But I can also view this as a problem with some context. So here I have a context which is saying n is a natural number, and hn is a name for the proof that 2 is less than or equal to n. In that context, maybe I want to try and prove this conjecture. These two statements I've written down here are equivalent. They're just different ways of writing the same thing. Okay, so I can now state mathematical questions, and in very simple cases, I can prove them. For example, 2 plus 2 equals 4. But we often want to do slightly more difficult proofs. So what do these proof expressions look like? Here are some examples of simple proof terms. If I want to prove true, I can use the proof term trivial, which tells me true is true. I can also, again, prove 2 equals 2 using REFL. So here are the first two proof terms I'm telling you about, REFL and trivial. REFL is the one which says something is equal to itself. So if I ever need to prove something is equal to itself, I can use the proof term REFL. And if I ever need to prove true, I can use the proof term trivial. These are very simple, but there are some more interesting ones, which are in the math library MathLib or in Lean Standard Library. For example, in the context where a and b are natural numbers, so I have a and b before the colon, and they're both natural numbers, so the space here just means I'm saying a and b are natural numbers, then what I'm trying to prove is a plus b is equal to b plus a. So to give a proof of that, I need to give a proof term. And it turns out that in the library, there is this fact already, nat.addCom_ab. If I hover over this, it tells me what the type of this thing is, and it matches exactly. So Lean is happy to accept this as a proof. Here's another example, a times b equals b times a. The proof looks very similar. And I include this example to show you that Lean has quite a robust naming convention. From the first example, you see it's nat.addCom, because it's on the natural numbers, it's about addition, and it's showing commutativity. And the second example, all I've done is change addition to multiplication, so it makes sense that the name is quite similar. So this is one technique you can use to guess proofs. There are more useful techniques, which we'll come on to in a moment. Now, I can also prove the very easy proposition I had earlier. If you don't remember what that is, I will use the print command to tell you what that proposition was. It's not showing on the same line. So my very easy proposition was a proposition that for every natural number, there exists a p which is bigger than my natural number n. And I can give a proof of that. I won't go too much into detail on what this actually means, but I can prove the proposition that I wrote down. Now is a good point to stop and talk about exactly what the difference is between my very easy proposition before the colon and after the colon. So when I wrote down the definition earlier, let me just move it down to make it a bit easier to show you. I was defining the proposition and saying it was a proposition. Now I'm giving an element of that proposition, which is a proof, and giving it a name, my proof. And therefore, I have proved as a theorem that this proposition is true. So just to check the types of everything once more, my proposition is a proposition, and my proof is a proof of that proposition. So my proof has this type, or in other words, it is a proof of this thing. Now, just using these proof terms gets pretty ugly pretty quickly. It's quite nice if you want to prove very simple things like true or a equals a. But if you want to prove something slightly more interesting, So here's an example of a plus a times b is b plus 1 times a. Writing out a proof term for that is pretty horrible. This isn't something you want to try and find yourself. So instead, we have tactics to help deal with this. Here are some very clever tactics which can do some pretty advanced stuff to try and find a proof. The first example here is the ring tactic. The ring tactic uses axioms of rings to try and prove your statement. And in this case, this is true for any ring, so it successfully finds the proof. Now, I haven't given the proof term here. Ring is a tactic which is generating the proof term on its own, and then, giving the proof. I then have simp and norm num. Simp is Lean's simplifier tactic, which can simplify simple things, and norm num is its numerical tactic. So norm num normalizes numeric expressions and can prove calculational things, such as 4 to the 25 is less than 3 to the 39. That point I will pause and check for any questions before I move on. Yes. Yes, there is a bit. So if you hover over the tactic, it tells you how to use the tactic. But if I right-click on it and press Go to Definition, then I can see exactly what the tactic is doing. This is not going to be at all helpful. I have no idea what this is saying. But the other thing you can do is ask simp question mark. Oh, okay, that's not a useful example. So simp, the best way to figure out what the tactic is actually doing is to hover over it and try and see what the documentation is saying. Sometimes they don't have enough documentation, but that's broadly what you want to do. So if you click on it, you can see its actual definition. Oftentimes that won't be so useful because it will be a bunch of Lean metaprogramming, which is what Lean uses to automatically generate these proof terms. But this does depend on what you're trying to prove. There are other tactics such as the show term tactic. Again, I don't think it will be that useful in this case, but you can get it to show you what proof term it gave. I'm not sure how informative that is. But in this particular case, you can see what proof term it generated. For more complex examples, I think this one might be a bit more horrible to look at. So yeah, it's a pretty long proof term. It's longer than the one I gave, but my one took some time to find. So there we are. Does that answer your question?
Yeah, and is there more on this in this conference? How Lean and how the strategies work?
Yes. Yeah, you can also ask people who will be able to give you more detailed explanation on how each tactic works. Each of them is basically written in their own way to help try and solve a particular kind of goal. Cool. Any other questions? Yes.
So it seems that theorem is also just defining an element of some pattern.
Yes.
So could you also use that instead of theorem?
Yes, you absolutely could. So I can just change this one to be a def of my example. And that would absolutely work. This is not usually such a good idea. And if I use the linter, which is essentially checking for code style, the first thing it complains about is that this is a def when it should be a lemma or a theorem. So what's happening here is that we usually use theorem or lemma to give elements of proofs and def to give elements of anything else.
Is there some real difference between those, or is theory just
the difference is that if you write theorem, the actual term that's on the right-hand side gets forgotten about, whereas def will remember it and be able to print it out later. So that's related to proof of relevance, which I'll talk about more in a second. But the difference between def and theorem is essentially whether it remembers the definition and can use it later on, compared to not. So if you are trying to give an element of a proposition, then you want to use theorem. Otherwise, you want to use def. Cool. Any other questions? Yes. Yes. So I'm using an extension called Errorlens. This is just a VS Code extension. I believe I'm not sure which of these it is. This one, there we the error lens extension on VS Code, which basically gives me any errors or warnings right next to the thing. The main reason I'm doing that, well, the main reason I like to do it is because it just puts everything in one place. The other reason I'm doing it for this is that the typical way of viewing these messages would be using the info view, which I'll talk about more in a second anyway. But the typical way of doing it would be to hover over this check, and it gives me the message on the right-hand side, which I can do for all of these. But that just makes everything a bit too small, a bit too cramped on the screen, so I didn't want to do that for this context. So yeah, the usual way of doing this would be to look in the info view, but with this VS Code extension, just makes it a bit easier. Cool. I think that was the same size. Any other questions? Yeah.
Yeah, so going back to the variables before or behind the code,
Mhm.
so they are equivalent, but is that for compiler or just for people?
I believe they're equivalent for the compiler. They just give the same term. Most of the time you want to, someone shaking their head. Am I wrong? Okay, good. Yeah, it's the same thing. Most of the time you want to put everything before the colon just because you can then name it, rather than inside the course of your proof you need to give each thing names. There are some cases where some tactics will fail if stuff is before or after the colon in the wrong way. But that means it's harder to automatically find the proof term. But the thing you're constructing is fundamentally the same regardless. Cool. Any other questions? Amazing. Okay. So how do we actually find these proofs in practice? Well, I've given you examples of these clever tactics, these high-powered ones like ring and norm num. But most of the time what we use in practice are much simpler tactics. The two most simple ones are exact and refl. But the first thing to notice is this keyword by. So the by keyword takes you from term mode into tactic mode. In term mode, which is the mode you're usually in on the right-hand side of a colon equals, you need to give a proof term. You need to explicitly write it out. As soon as I use by, I'm into tactic mode. At this point, I can start using tactics, which will help me automatically construct the proof term. But exact does the opposite. It takes me back from tactic mode back into term mode, which feels like I'm going the wrong way, but it's sometimes useful if I know the answer anyway. So by exact is doing exactly nothing here. I can delete it and everything works fine. By refl is also a tactic. So earlier we saw it was a proof term. It also turns out it is a tactic, which can prove roughly the same things that refl can. The refl tactic can, sorry. Okay. But in practice, we write tactic proofs. So let me try and give you an example of what this looks like. I'm going to have to zoom out a little bit so this is readable. Okay. What I will do, I'll zoom on the right-hand side a bit. Okay. So this is the info view. This is what Lean will look like, and Lean will tell me when I'm trying to write a tactic proof. I have the goal state on the right-hand side. It tells me I have one goal to prove. In the context, I have a and b as natural numbers, and the goal is a plus a times b is equal to b plus 1 times a, which matches exactly what I claimed to be proving. And I have this keyword by, which is starting my tactic proof. Now, the tactic I want to introduce here is the rewrite tactic, which is written RW for rewrite. And the rewrite tactics lets me rewrite with equality lemmas. So add mul is a lemma in the library which says that a plus b times c is equal to a times c plus b times c for natural numbers. I am then rewriting with this tactic, and Lean is changing my goal from what it was originally to b times a plus 1 times a on the right-hand side. So you can see from red to green what's changing here. And this is exactly what the rewrite is doing. It's rewriting using this lemma in the goal to make it something hopefully easier to prove. The b1 and a here are the instantiations that I want to give for the a, b, and c variables in this case. Okay, so really what I want to do to prove this is, well, I want to expand the right-hand side. I want to do 1 times a is equal to a. Then I want to do some commutativity to make it all line up.
How do we
By default, it turns the left-hand side into the right-hand side. So in this case, add mul as a lemma does a plus b times c into something. And so that's exactly what this is doing what b plus 1 times a and turning it into the other thing. But if I do the same thing with a left arrow before it, it will do the exact opposite and turn it back. So I can rewrite with the inverse of add mul, and it will do the exact opposite and return. So this is what it is before in red, and then after it gives it back. The way to write this arrow is using \L. That lets me write that arrow. So you can see I've also used this Unicode symbol for the natural numbers, for the real numbers earlier. I've used a couple of them throughout the file. There are oftentimes ways of avoiding the Unicode symbols, but usually in Lean we prefer to use them, at least in Mathlib we prefer to use them. And if you're unsure how to write it, you can hover over it and it tells you how to type it. So in this case, I hover over the left arrow, and the first example is what I use there of \L lets me write it down. And yeah, as this is also telling you, rewriting with the theorem goes from the left to right. Rewriting with left arrow in the theorem goes from right to left. Cool.
If I have a larger equation and I have several a's and several b's inside, so
Yeah.
which a is all of them?
Lean will replace all of the a's by b's in that example. There are tactics which let you do only the first one or only the third one, if you like. But by default, it will change every particular matched instance on the left-hand side to the right-hand side. Now, I want to try and be clear about what that means. So here, I've specifically used addmul b1a. So it's specifically, let me just use the first example. It's specifically looking for patterns of the form b plus 1 times a. If that expression is in the goal multiple times, it will rewrite all of them. But what I can do is not actually specify b1 and a. Let me first get rid of this second version. I can also not specify b1 and a, and Lean will try and search for anything which matches the left-hand side pattern a plus b times c. In this case, it finds, because it's exactly one anyway, it still finds the correct one and does the rewrite. The reason I mention this is that if there are multiple instances of this pattern a plus b times c, it will only rewrite copies of the first pattern it finds. So here I had b plus 1 times a. If I also had c plus 1 times a somewhere else, that wouldn't get rewritten by this first addmul call. But if I had b plus 1 times a somewhere else in the goal, that would get rewritten. Does that make sense? So it's every instance of the first pattern it finds. Hopefully that shouldn't happen too much. In practice, it's surprisingly rare for that pattern to appear that often that this is problematic. But if it is problematic, there's the nth rewrite tactic, which should work. And there are also other tricks to get around this kind of thing. OK, cool. So now that I've changed the right-hand side to be 1 times a, I want to simplify 1 times a. I happen to know that the name of that lemma is 1 mul. We'll talk a bit in a second about how you might guess that if you don't know what it is. But just again, we can see this has changed 1 times a into a. I can then keep going. I can see to solve the goal, I want to do commutativity of addition somewhere. So I can use add com, which is something we saw earlier, to turn the left-hand side a plus a times b into a plus b times a, and then use commutativity of multiplication to finish the goal. And then I have no more errors, no more goals, everything's good. OK. So at this point, there's this example file, S01 calculating, which is in this repository I mentioned earlier. That has many more examples of tactic proofs using rewrite and a little bit more information on how rewrite works. So by this point, I think it's reasonable for people to be able to finish this file, but I'll keep talking for the moment anyway. For the record, by the way, if you do try this file and you get bored halfway through, feel free to just move on. You don't have to do all the examples. You can do whichever ones you are interested in doing. Okay, so rewrite is a very useful tactic. And here is an example of a more complex proof. I'm not going to step through exactly what this is. But here we're proving Euclid's theorem that there are infinitely many primes. So the statement is, in the context of a natural number, there exists a p which is more than n and is a prime. And here is a tactic proof of that statement using some tactics like let and have, and then this key thing exact at the end. Now, that's not the only way of writing this proof. I could also give it as a term mode proof. So here I haven't used the keyword by anywhere, but I can still give the proof. Now, this second one is pretty clearly much harder to read. It's not as clear what's happening. Even in the first one, if I don't really tell you what it means, you can see roughly what's going on, that I'm making this thing called p, proving that n factorial plus 1 isn't 1, proving that n is less than or equal to p. In this, it's really not clear what's going on. But to Lean, the proof doesn't matter. So if I ask it, is Euclid theorem, so this type, sorry, the element of this type, equal to the element of this type, Lean thinks they're exactly the same. Because remember, REFL tries to check if two things are exactly the same and gives you a proof that they're the same if they are. And Lean thinks these proofs are exactly the same. This isn't specific to these particular proofs I've written down. If I find any two proofs of the same thing, Lean will, by definition, believe they're the same. Yes. Sorry. REFL is a proof term. BiREFL is a tactic. The general difference is that REFL will prove things like A equals A, B equals B, whereas BiREFL will also prove things about reflexive tactics, the reflexive relations, sorry. So for example, A if and only if A is something that BiREFL will be able to prove, but REFL won't be able to prove. There are also some more complicated differences, which I won't go into, but REFL briefly proves reflexivity of equality. BiREFL proves reflexivity of any reflexive relation. Yeah.
So this is, if I would have used definition instead of theorem, this would not have been equal.
It still would be equal. No, it still would be equal. Because these are both propositions. And all propositions of the same type are equal.
Okay.
Yes.
The type of proposition knows that there's only one element.
Exactly. Exactly. Yes. So what's really happening here is at runtime, any proof is erased, and so they're just viewed as equal, regardless of whether you called it a def or a theorem. Cool. And then here's my second reference that this file has some more examples of tactic proofs. Okay, yes.
Are there any tools that exist that like partially justify something like the way you could split theorem to the
Not that I know of right now. I think there are a couple of people working on code formatting to make it a bit nicer. Right now, there's not really nice ways of doing that. It should be feasible. I think no one's just spent the time to do it yet. Yeah, on that note, it is, so I said here the proof doesn't matter to Lean, but the proof in some sense does matter because if both of these proofs are in a library, this one is easier to understand than the second one, which also means it's easier to maintain. If someone, for whatever reason, changes the definition of prime, it's easier to fix this first proof than it is to fix the second proof. So in Lean's standard library, MathLib, in Lean's standard library for maths, I should say, MathLib, we generally prefer more readable proofs compared to these hyper-condensed or sometimes called golfed proofs. That's not a general rule, but oftentimes it's nicer to have more readable proofs. So yeah, the proof doesn't matter to Lean, but it could still matter to people. One of them is easier to read, one of them is easier to teach. We had the nice example from earlier of being able to step through a proof with the help of Lean. That wouldn't really be possible with something literally written like this. Okay, and then this second file, so this is in the basics folder. There is sections 1 and 2, calculating an overview, which give you some more examples of tactic proofs so you can see what they look like. Okay, so some more tactics. Here is a tactic called exact question mark. Now remember, exact was something you could use to go from tactic mode back to term mode. And then that asks you to give an exact term which closes the goal. but maybe you don't know what the exact time is. So you can ask exact, and it will try and guess what the proof time is. In this case, it tells me the correct answer. Ooh. So by exact question mark, we'll try and search through the library and find something which matches. In this case, it's matched my earlier one, Euclid theorem, which successfully closes the goal. So if you expect that there's something in the library which should exactly match your goal, you can use exact question mark to try and find it. So I'll put that back for the sake of. Now, similarly, sorry, one sec. I accidentally broke that example. So I'm just going to change this back to example. Sorry. Okay. So earlier, I used the rewrite tactic with some lemmas which I happen to know exist, like 1 mul. Let's say you don't know what these lemmas are called. You don't know how to find them or how to use them. There's a tactic rewrite question mark, which will try and help you find rewrites to solve your goal. So we have these tactics exact and rewrite, and exact question mark and rewrite question mark, which aim to make it easier for you to find the lemma you need to be able to do exact or rewrite. In this case, when I do rewrite, my info view is filled with suggestions. The first one it suggests is rewrite with nat.addMul, which is essentially what I did already. I can click on that. It then changes my goal using that rewrite to be 1 plus a. But now let's say I don't remember the name of the next lemma. I can ask rewrite again. This time, it's not quite as helpful. It suggests doing the opposite of what I just did. Not ideal. It gives me many more suggestions. The second one is also kind of rubbish. But if I scroll down enough, I do find something useful. So this lemma would help me. And yeah. OK, the next thing I want to mention is the example you gave earlier of I've made this set, singleton 1. I've managed to make my set. Can I prove that 1 is in my set? Well, let's say I don't know what it is. I can try using exact. Exact tells me REFL will close the goal. And yeah, it closes the goal. Amazing. The lemma that you, in some sense, should be using here is set.memSingleton. So what's this lemma actually saying? Well, I can use check to tell me. It's saying that if alpha is a type and A is an element of that type, then A is in the singleton set of A. And so set.memSingleton will prove that 1 is in singleton 1 as a set. OK, so that answers the question from earlier of how do you prove that. OK, so yeah. Exact and rewrite are some of your bread and butter tactics, and putting a question mark after them can make it slightly easier to use them. Yes? Yes, that's a good question. OK, so to answer that, we need to look at exactly what all these definitions are saying. So first, let me try and step through this. My goal at the beginning was prove that 1 is in my set. I'm going to first rewrite with the definition of my set. So my goal looks like 1 is in 1. But what's the definition of membership and the definition of this set singleton 1? Well, if I, oh, that's not helpful. If I do simp question mark, oh, OK, that's also not helpful. This is not, there we go. If I do rewrite question mark, go away. It tells me this lemma, rewrite mem singleton if, and that closes the goal. Let me, OK, let's not worry about why that does that for a second. Sorry?
I think one explanation would be to just that the singleton set is defined as being the subset of all elements that are equal to that specific element.
Yeah, I was hoping to control click to the definition, but I couldn't get there fast enough. So the definition of the singleton set, I can't find it off the top of my head. Which one, sorry? The simp command or synth? Ah, yes, I see what you mean. It'll be that, right? OK. There we are. So the singleton set is defined as the set of elements B where B is equal to A. Then to be in this set, all I need to do is prove that B is equal to A, which in my original case was prove 1 is equal to 1, and we know that REFL should close that. So this is because of the way singleton is defined, it's only asking for a proof that 1 is equal to 1, so REFL should work. Yeah, thanks for that, Eric. The other thing I want to mention here, yes?
Would the same proof work if we had set 1, 2?
No, because, so if I change this to 2,
No, sorry. If the set is not singleton, but contains 1 and 2.
Sure.
I asked if 1 is there.
The same proof wouldn't work, so doing something like REFL doesn't work, because this set isn't defined as being equal to just 1 anymore. It's slightly more complicated. I can still use the simp tactic to try and prove it anyway. Okay. First, I rewrite with my set, and then I use simp. Now, what did simp do? I can use simp question mark. Now, while exact question mark and rewrite question mark help you find lemmas, simp rewrite also helps you find lemmas, but simp question mark, sorry, also helps you find lemmas, but in a different way. So remember, simp is lean simplifier, and if I do simp question mark, it will tell me which lemmas it used to do the simplification. In this case, it used these two lemmas, mem singleton if and mem insert if. These two, as you might be able to guess from the name, characterize what it means to be a member of an insert set and a singleton set. But essentially, the simplifier is able to prove this, but you need a slightly more difficult proof in order to get there. Yeah.
What was hash sync?
Okay. So we had hash check, which tells you the type of something. Hash print, which tells you the definition of something. And then hash synth will use, okay, sorry. Lean has a type class inference system, which I won't talk too much about, but essentially when you have notation, it needs to figure out what this notation actually means. In this case, what does this singleton notation 1 mean? The singleton notation is defined by the singleton type class. And there is some instance somewhere which says that there is notation to let natural numbers be singletons of sets of natural numbers. Synth says, where is that definition? So what synth will do is it will try to find the instance which checks this. And synth will find and name that for me. So synth does type class synthesis and tells you what it synthesized together, which is why it's called synth. Yeah, I'm not going to talk too much about the type class system. I think someone else is going to do that. It's a little bit out of scope for this. Yeah. Okay, cool. Eric will tell you more about type class system and hopefully explain synth better than I did. Am I out of time, by the way, or should I keep going? Okay. I'll give you a slightly more interesting proof then. And along with that, we'll give you a slightly more interesting definition compared to the slightly boring ones we had earlier. Here I've defined, yes?
Is there something like rewrite question mark with more than one step of the
No, but you can, after the first rewrite question mark gives you an answer, you can ask rewrite question mark again and try and get a second thing. But something like simp will keep doing rewrites as much as it can, which kind of satisfies that. Not completely, but it kind of helps. Nice. Yeah, all of these tactics are very rapidly improving. So if there's something you think would be helpful, it might be worth mentioning on the Zulip chat, and someone might just do it this week. That's entirely feasible. Yeah, any other questions before I move on to another definition? Yes?
Yeah, instead of proving set example for 1, 2, if we write 1, 1, which is still the singleton sets.
Yeah.
Will the original proof still work?
No, it won't, because Lean can't by definition say that it's the same set. If I use a simplifier or I use some tactic, it will be able to prove they're the same thing. But by definition, they're not exactly the same thing. I think this proof would still work, though, the same one that was for 1, 2, for essentially the same reason that it did for that example. But by definition, these are slightly different things, so it makes sense that they shouldn't be exactly the same. Sorry? Yes. So the simp tactic will try and simplify using a bunch of lemmas in the library which are tagged as simplification lemmas. So what that really means is simp is, in some sense, searching the entire library for something which it thinks could be helpful. And this, in principle, could be slow, especially if there's lots of things you need to do or there are lots of things imported. Simp only will only use the lemmas I've named to try and simplify the goal, rather than try and search through the library to find everything. So simp will use any simp lemma in existence, and also anything inside the brackets. Simp only will only use the things in the brackets, which is why it's called only. Simp question mark will run simp, do this search through the library of everything it can, and then tell you what lemmas it actually used to use in simp only. So this is simp question mark and simp only are valuable for one, because they're just more efficient, and so it makes your proofs run a bit faster. They're also a bit more stable. So if someone adds a new simp lemma to the library, it, in principle, could slow down your proof or make your proof break because it's a simplification in the wrong direction. Hopefully that shouldn't happen, but in principle it's possible. But with simp only, that's just disallowed because it only uses things in the brackets. Cool. So I mentioned there's simp, and there are a bunch of things in the library which are tagged as simp. And this is essentially a human curated list using things we think would be useful. Let me try and pull up an example. Let's see this one. Maybe that's not a great example. Which of these will be sufficiently simple? Maybe I should look in the add in this file. Simp. Okay, here. So this is the theorem that says if n is a natural number, and this is actually in Lean's core rather than standard library. So in Lean's core, they, in general, prefer not to use the Unicode notation. So it's written as nat instead of n, exactly the same thing, just written differently. And this is the same when n minus 0 is equal to n. And this lemma is tagged as simp, which means that any time you have n minus 0 in the goal and you try and use simp, it will hopefully find this lemma and rewrite with it. And there are many things in the library which are tagged simp. Cool. Any other questions? Yeah. Yeah. Okay. Protected means it's. Is someone else going to talk about namespaces? No, I'll talk about namespaces. This lemma is called sub-zero. And if okay, let's say I hover over this one. It tells me its name is nat.ltsuck_le. Yeah, it tells me what its name is, and its name is nat.ltsuck_le. It's got this nat prefix, meaning that if I call something else ltsuck_le, it hopefully wouldn't clash because that thing doesn't have the nat prefix. But if everything I care about is using nats, I can use this thing called open real. Or open, in this case, it would be open nat, which maybe I did later on. Oh, I actually have done that already. So open nat is something I did back when we were talking about rewrites for the first time. Open nat tells Lean, okay, if you can't figure out the name of something, try and put nat before it, and then try and get the name. Protected does the opposite of that and says, if you need to name this lemma, you must write nat dot in front of it. Now, that wasn't the clearest explanation, but hopefully that makes some sense that namespaces make it easier to name the lemmas you're talking about, and protected gives you a little bit more control over how that works. Essentially, this is just a naming thing rather than anything fundamental to how Lean works. It's like, this is more relevant to how do you structure the library well and structure the library in a way which is nice to use rather than anything foundational about Lean. Yeah.
What belongs in Lean's core versus standard library versus that?
That's a good question. In some sense, it's based on what the different people who use each thing are interested in using. So there's not necessarily a hard and fast rule. Mathlib is usually more mathematical things. So more complicated structures, definitions, theorems, like something you'd more commonly see in an undergraduate course, whereas the standard library has something of a more computer science lean to it. No pun intended. It's got stuff about like arrays, lets you prove things about arrays. I'm not sure if I can get an example efficiently here. Okay, standard library, standard data array. Oh yeah, so here we have hash maps, lists, option, range, red, blue maps, binomial heaps, that kind of thing, which is often the things useful if you want to use Lean as a functional programming language rather than as a proof assistant. There's obviously some overlap, but broadly that's something like the difference. And the stuff which is in core Lean is stuff which is kind of fundamental to Lean itself, like the natural numbers themselves, and that kind of ultimately basic thing. So stuff like the definitions of the most basic tactics, maybe even like the definition of theorem. So these are the much more fundamental things. So it is this hierarchy of Lean's core, and then Lean standard library, and then MathLib, the math standard library. Cool. Any other? Yes. I don't know. I don't have a good answer to that. Sorry. Anyone know? Why is Sub-Zero protected?
I think the global sub-zero one is the one that's valid in rings. The subtraction on that is very
Oh,
behaved algebraically because
that's true. Yeah.
3 minus 5 is 0. It just cuts off at 0. And so I guess
Yeah. So
names are for the better behaved version.
yeah. So yeah. Say that again. Sorry. Yes. Yeah, so protected will only change something if you've already done OpenNat. If I haven't done OpenNat, protected is completely irrelevant. Cool. Okay. Any other questions? Yes. Mm. Yes. Ah, that's a good question. It's very related to what you asked earlier, actually. So I mentioned earlier that rewrite will find one pattern and rewrite every instance of it. Simp only with one lemma will find every instance of that pattern and rewrite with every instance of it. Oh yeah, and it will keep doing it. And this, in principle, could create loops. For example, if I use add_com, then it could go back and forth. Simp has a trick to try and make sure it doesn't loop. You can still make it loop if you try. But it will keep doing this rewrite as much as it can, rather than just once like rewrite will. Yeah, thanks for adding that. Yeah. Mm-hmm.
What was the meaning to have that? I mean, that kind of makes sense. But...
Okay, so I think this is more going into the next session rather than this one, but I'll mention it briefly that have lets me create a proof of something locally. So in this case, I want to prove that n factorial plus 1 is not equal to 1. And on the right-hand side, I'm giving its proof term. Now, on the next line, I have this statement in my goal, in my context. So have lets me prove something auxiliary and then use it later on in my proof. That's what the have tactic is doing here. So the next line, I'm creating a proof that P is prime, which turns out to be this particular term. And then on the next line, I have in my context that P is a prime number. So have lets me introduce facts locally into my context. I think hopefully if I hover over it, it tells me that as well. So have adds the hypothesis to the current goal if you've given its proof. Yeah. Cool. I feel like by this point I must be over time. Sure. It's up to you. Okay, I don't have much more left, so I'll try and do this quickly. Okay, so I wanted to give you.
You have to have something.
Okay, perfect. Amazing. Okay, so here is a definition of the factorial function. There is a version in MATLAB already, which we used for the Euclid's theorem earlier, but I wanted to give you a definition by hand so you can see what it looks like, and so you can see what it's like to prove some stuff about it. The factorial function is defined recursively in maths, so it's defined recursively in Lean. I'm saying at 0, it's defined to be 1. At n plus 1, it's defined to be n plus 1 times my factorial of n. There are a couple of things going on in this definition. Firstly, I'm defining it by cases on natural numbers, and Lean can see that this is a complete definition because I've covered the 0 case and the successor case. The second thing that's happening here is it's a definition by recursion, so in principle, you need to show that it terminates. Lean can check in this case that that happens automatically, and it knows that because when I'm trying to give an element of my factorial n plus 1, so trying to give the value of my factorial at n plus 1, I'm defining it in terms of my factorial of n, which is the previous one. So the argument has gotten smaller, and Lean is happy to take this as a proof of termination. It's not true in every case that it can infer this. You can sometimes, or in the case when it can't automatically figure it out, you can give the proof or give a more difficult relation to show that it's well-founded. I won't talk about it too much, but here is a way you can define simple functions like this by recursion. I can then check that it has type n to n. Now, this arrow is not something I've talked about, but in this case, you can just think of it as a function arrow. I've given an element of the type of functions from natural numbers to natural numbers, which makes sense because factorial function takes in a natural number and gives you back a natural number. Now, there's another hash which is sometimes useful, which is eval. And this is using Lean to compute rather than to check proofs. So here, Lean is evaluating my function at 10 and giving me the value 3 million, or roughly 3 million. Eval is useful for sanity checking definitions. So when I was actually writing this file, I accidentally put an n here, and it told me that factorial of 10 was 0, and I realized something was dodgy. But it's also useful if you've used Lean as a functional programming language, you can then use eval to essentially run the program you've written, just like you could use in Haskell. Just like you can run a Haskell program, you can use eval to run your function. Okay, so let's prove some simple things about this definition. The first thing I want to prove is that my factorial of n plus 1 is n plus 1 times my factorial of n, which it hopefully should be. And indeed, that's the definition. So REFL will do that because that's just true by the definition. The two sides are exactly equal. Similarly, you can prove that the factorial of 0 is 1. Again, that's by definition, so REFL is happy to do it. Here's something more difficult, though. I want to prove the factorial is always positive. Well, factorial was defined by induction, so it makes sense that I want to prove it by induction. So I'm going to use this tactic, induction prime. The reason there's induction prime and not induction is induction prime matches Lean 3's induction. There's also a Lean 4 induction tactic, but I want to demonstrate the induction prime version because I think it's a little easier to explain for the moment. Okay, so induction prime n does induction on n. I'm then left with two goals on the left-hand side. First is the 0 case, and second is the successor case. So in the 0 case, it's asking me to prove that my factorial of 0 is positive. And in the second case, it's asking me to prove that if I know that n factorial is positive, then n plus 1 factorial is positive. Okay, well, the first case is easy. I know that factorial of 0 is 1, and then I can just simplify. There are many tactics that could solve this last thing. For example, norm num would also do it. I could give an exact term mode proof of this, but I don't really want to. Simple do it, so simple do it. In the second case, I want to prove that 0 is less than factorial of n plus 1, or factorial of n plus 1 is positive. Well, this says successor rather than n plus 1, so I want to change that. Using this lemma called suck equals add 1. This is saying that successor of n is equal to n plus 1. Now I can use my lemma from earlier, saying that factorial of n plus 1 is n plus 1 times n factorial. Now my goal looks like this. It's saying that n plus 1 times my factorial of n is positive. I want to prove now that This is positive because each of its components are positive. If I multiply two positive numbers, I get a positive number, which makes sense. The way I use this fact is using the apply tactic. So there are two new tactics I've introduced in this proof, which is induction and apply. Apply lets me apply this fact in order to split the goal into two more things. So after I've used this apply, I have two things to prove. First, that n plus 1 is positive, and second, that n factorial is positive as well. So if I hover over the type of molpos, it's got some nonsense at the beginning, but what's important is if I have a is positive and b is positive, then a times b is positive. So I use apply to apply this fact, and I'm left with these two goals. Now, how do I do this? It turns out that suckpos will work, but if I didn't know that, I could use exact question mark, and it tells me the same thing. And finally, this last one, I have in the context that IH is a proof that my factorial of n is positive, and I know that is exactly the thing I'm looking for, so I can use exact IH. This is an example where the exact tactic, even though it seems a bit counterproductive, I'm going from my tactic mode back into my term mode, it's useful for this kind of thing when you have an exact match. There are other options I could do here. For example, assumption. Searches for any assumption in my local context which matches. But I'm going to stick with exact for the moment. Okay, and then for the sake of completeness, I want to show an example with induction rather than induction prime for any people who don't like the induction prime version. The difference between these two is essentially the syntax you use to write them. In almost every other way, they're the same thing. It's just a syntax you use to write these two tags are the same thing. Slightly different, sorry. Okay, so that's the main stuff I wanted to cover. I want to add a personal note at the end, which is related to what we were talking about earlier with the unit fractions project, which is that these are very simple proofs. I haven't proved anything particularly interesting here, but this does scale incredibly well. So this conjecture of Erdős and Graham, I'll tell you very quickly what it is and its history. It was first posed by Erdős and Graham around the 1980s, maybe before that, but it was definitely in print in the 1980s, so it's at least that old. There was some partial progress published in the Annals of Maths in 2003, and then it was fully sold by Thomas Bloom in December of 2021. There was a Quantum magazine article about it, January 2022, and Lean knew about it by June of 2022. So that's within about 6 months. Tom Bloom and I had fully formalized this proof, and fully formalized this proof, his entire paper. And I can actually, luckily enough, working in combinatorics, the statements are usually fairly easy to understand. So I've given you a rough idea of what the statement is here. Given a set of natural numbers, you can define its upper density. This is a particular kind of limit. If you don't know what that is, don't worry too much. But the rough idea is, if I take all of the even numbers, that has density a half. If I take all of the multiples of 3, that has density a third. If I take all the primes, that has density 0. So that's some vague intuition about what this density thing means. The statement is then, if I have a set of naturals with positive upper density, then there exists a finite subset of it. So there exists a finite subset of the natural numbers, which is a subset of A, such that if I sum the reciprocals, it's equal to 1. So this was an open problem for 40 years or so, and we've fully formalized the statement. Now, one thing which Alexander was talking about earlier is that the referees now, in some sense, only need to check that the definitions make sense and the theorems make sense. And that's particularly important in this example, because when I did this formalization, I had to define upper density, because that was in MATLAB already. I could have defined the upper density to always be 0. Then this theorem is completely vacuous, because I'm assuming that 0 is less than 0. So this should be very easy to prove. So just because I have formalized this theorem, there is still some work to do to make sure all the definitions are correct. I haven't cheated in some way. But you don't need to necessarily check that my proof is completely correct because Lean is doing that part. So the humans still need to, in some sense, check the definitions, but not all the proofs. The other thing I want to mention very quickly is a project I'm currently working on, which is the new upper bound of diagonal Ramsey numbers. This was first posed in around 1935, maybe earlier. Again, there was some partial progress in the Annals of Maths. in 2009. Ooh, okay, luckily I'm actually finished this time. Improved bound on this appeared in the archive in March this year. Again, a Quanta article in April this year. And hopefully Lean should know about it within the month, provided my month goes well this month. And this is what the statement is saying. There's this function called the diagonal Ramsey numbers, which is just a function from natural numbers to natural numbers. And the claim is that this function is bounded by 4 minus c to the k. Previously, it wasn't known that there was a constant here, a positive constant here. So this is a new result, which wasn't known, since 1935. Okay, so let me quickly summarize what I've talked about. We have expressions and types. Every expression has a type. And if you have a proof, its type tells you what that thing has proved. I've given you some of the most useful tactics, in my opinion, or some of the easiest to explain at the beginning, which is rewrite, exact, apply, simp, and induction. There are also some more heavy tactics like ring, norm-num, positivity, and linearith. Ring and norm-num we talked about already. Positivity will let me prove, often let me prove things about things being positive. So for example, here, I had to prove something is positive, and if I use positivity, then it's happy to finish the goal. So positivity is very good at proving things are positive. Also works for non-negativity and non-zero, just using the same keyword, positivity. Linearith is another heavy tactic, which is often very useful, and it proves things about linear arithmetic. There's also the refine tactic, which I won't say much more about. It's fairly similar to apply, but it's also a tactic I use a lot. Okay, then there are more examples in the files I mentioned, so S01 and 02. There are some more examples in there, and there are further examples in files 3 to 6. Again, these are useful if you want to do them. If you get bored of some example, feel free to skip it. There's just more examples for you to have a look at and see what these things are like. It also explains 2 other features of Lean, which I didn't talk about, which is curly braces and calc, which are good to know about, but not super important for right now. Okay, that's everything. Any questions? Yes.
So in your one of the classes, there was an up, no, so theorem, there's an upper row called B.
Yes. Okay. That's a good point. So if I don't have the up arrow, Lean complains because A is a set and B is a fin set, and it can't automatically figure out how a finite set should be a subset of a set. The up arrow is saying, well, it's a finite set, so it's a set, so just treat it as a set. So the up arrow is called a coercion, and it's converting my finite set into a set in order to do subsets notation.
Does up arrow in general somehow guess what you mean in such a situation? Or is it
Yeah, pretty much. The more principled way of doing this would be to tell Lean what it should be guessing it should be lifting the type into. So I can say treat B as a set in this particular context, and Lean will then write it with an up arrow, but I, in this case, get to specify exactly what it should be. Yes, exactly. And that's actually kind of what I'm doing later on here. So if I didn't have this colon Q, then it would treat this as natural division. It would be 1 divided by the natural number I. And natural division is very weird because if I is at least 2, 1 divided by I will just be 0. And so again, I've proved something not very interesting at all. But when I tell it this is in Q, it puts the up arrows in the right places so that it treats 1 over I as a rational number and does something actually interesting. Yes?
Presume this won't work with any good-like exercises like fit set defined as a subclass of set.
Not in this particular case. I think, again, someone later in the week will be talking about how those things work in general for algebraic structures. But you're completely correct, this doesn't work for general types. But what's happening here is this up arrow is notation for a coercion, which is It has co, right? Anyone? Just co. Oh, sorry, I mean the type class. Oh, it is called co. Okay, so there's a type class called co, whose elements are things which can be lifted to other things. So there is an instance which lets you lift fin sets of natural numbers to sets of natural numbers. Oh. Essentially, the answer is, yeah, you can't lift anything to anything else. There are special things which you can lift. The code T, the T is for transitivity. So that means if you can lift like A to B and B to C, then it can also lift A to C. But the things which can be lifted to other things are defined in Lean, specifically in a particular way. So in this case, the coercion will be just look at the elements of the fin set, and that is itself a set. So that's how you can view any fin set as a set. Similarly, you can view any subgroup as a subset, any natural as a real, but these are defined in Lean. They're not just, I can't just do magic. Ah, perfect. Yes. Okay, I was hoping for, yeah, okay. I was looking for this actually, but yeah.
Important to like say that we don't always have to go into these enough lines of things.
Yeah. Yeah, it's not so important how these things are defined. Although that does mention something I did want to say earlier, which is you can click around the info view, and that's often very helpful to see what's happening. So in this case, we as humans know that when I've written A times B, I'm doing the A times B before I'm adding A. This isn't A plus A in brackets times B. We as humans know that. Lean is also clever enough to know that. But I can also double check. If I hover over A times B, it's highlighted that section, showing that it has grouped those things together. So if you, what this is really doing is looking at subtrees of the syntax tree and highlighting those. So if I highlight over A, I should have